Hi everyone, this is the second in a series of videos where we talk about how to code up a GPT model from scratch. We are going to look at the GPT-2 model, which nicely fits within the CPU. Here we have a Colab notebook which, as you can see, runs in a CPU, and we are able to call a Python function which sort of generates the next token, and as you can see, it runs fairly fast on a CPU. Even though it's a full-fledged GPT model. Of course, it's GPT-2, so it's not the best model, and as you can see, it sort of starts repeating itself after a while. But our goal is to learn how the GPT model works from scratch. And just to give you a little bit of context, what this notebook does is that it loads the GPT-2 model weights, which pre-trained weights from the GPT-2 model. It sort of constructs all of the functions on creating the architecture of the model, as you can see here. And this is what we are going to go through in this video. And then it sort of loads the weights here in this load weight function, and finally allows us to generate the next token prediction. We'll use a few sort of resources along the way. One is the illustrated transformer from JLMR, which is one of my favorite places to learn about large language models, and then the attention is all you need paper, and then this amazing repository from Sebastian Rachka called LLMs from Scratch, which is where I sort of copied the implementation here from. And this is basically the same implementation as in this repository if you want to sort of follow along here as well. In the last video, we had looked at the multi-headed attention module in the GPT-2. In this video, we are going to look at the GPT model itself. Okay, so let's start by loading the GPT-2 model. There are a number of available models here. We have loaded the GPT-2 small, which is, the smallest possible one because I did not want to use a GPU. But our goal is to understand what this model does. If you choose this model and you load the pre-trained model from Hugging Face, you get this nice sort of explanation of the architecture. And to me, this is like really important. And the first thing I want to do is to sort of go over this architecture, and then I'm going to show you how this is sort of implemented in Python here in this function. So let's go over the architecture, and the architecture should be familiar to you. So we start with, let's go to the illustrated transformer. And as you know, what happens here is that the GPT-2, this is an encoder only model, so let's forget about the decoders. So we start with these, these inputs, and these inputs pass through a series of encoders, and then we get a next token sort of prediction. Let's see where we are. Okay, so the first thing that happens is that we get an embedding. A word embedding which we learn, and 50,257 is the size of the vocabulary. So for each word in the vocabulary, we learn a 768 sized vector, which is why this embedding is 768 size. And then we have a positional embedding. So the context in this model is 1024, which means that you can sort of send 1024 tokens. So like here we have 3 tokens. You can sort of send 1024 size tokens to the encoder. And for each of these tokens, we have a corresponding sort of positional embedding. And if you want to learn more about positional embeddings, I think this resource has some explanation of what a positional embedding looks like. And basically the idea is to encode the pattern that this word comes after this word and so on. So we have these 2 embeddings, and then there is a dropout layer. And finally, we come to this module list, which is this GPT block. There are 12 such GPT blocks. So the GPT blocks looks something, if we look at the attention is all you need paper, the GPT block looks something like this. Yeah. So as you can, in this paper as well, you can see the input is sort of these word tokens, and then you have the input embeddings, one for each token, and then you add these positional embeddings, and then you go to these layers. So we have 12 such layers here. So nx equal to 12 in this case. And in each of these layers, there is a multi-headed attention, add a norm, feed forward, add a norm. So let's come back here. So here there is first a normalization layer. So it takes these 768 vectors, sized vectors, and normalizes them. And then there is the GPT attention layer. There is a self-attention layer. Then there is a projection, which is just a linear sort of layer. And then there are sort of two dropout layers here. And the self-attention layer is this layer. And then there is the feed forward layer, which is this second projection layer. Why does this attention layer say 2304 into 768? It is because 2304 is 768 multiplied by 3. So for each of these attention layers, we need to learn sort of three sets of vectors, the Q, the W, the Q, and the query key and the value vectors. And you can see this when we load the weights here. So when we take sort of this GPT from the Hugging Face, and then we start loading the weights, you can see that we split the attention weights, the bias, and we split the attention weights into the query key and the value weights. So we learned sort of 2304 into 768. And then we have the projection, which is just a linear layer. And that is what the attention consists of. And we have 12 of these. So that is, it says 12 multiplied by GPT2 blocks. So we have like 12 of these layers stacked together, or the illustrated transformer has a nicer picture. So we have like many of these stacked together, so 12 in this case. And then we have the GPT to MLP, and basically that's a little bit different from what's happening here, maybe. And that is a this is basically how it looks like as a mathematical equation. So first we take a linear projection of expanding 768 to 3072. So 3072 is 4 into 768. So we expand it 4 times, and then we again we apply the GLU activation, or the GLU activation, and then we have another sort of linear layer which contracts it back from 3072 to 768. So we're back with a 768 sized vector, but we have a lot more weights which we learn which helps us to create a better model. And then we have a small layer norm which I think gives us the final after that we get the final logits. So that's what the structure looks like. Let's see how it's implemented here. So in the last video, we went through what the multi-headed attention does. And we won't go through it again, but essentially we take these vectors, tokens, each one has an embedding, we pass it through the attention, we get another set of embeddings, and then we pass those embeddings to the feed forward layer. So let's see what, so maybe it's instructive to see at this point. The layer norm is pretty clear. It just divides the, normalizes the activation by subtracting the mean and dividing by the variance. The GLU is the GLU activation, which is similar to the ReLU, but it's multiplying by X multiplied by the Gaussian CDF, which is sort of similar, looks similar to what the ReLU does, but it's differentiable. And then the feed forward layer, as I was saying, it sort of has two sequential linear layers. One is it goes from like the embedding dimensions, which is 768 here, to 4 into 768, and then applies a GLU, and then applies like 4 into 768 back to 768. So now we go to the transformer block, and the transformer block is basically this one here. So we have 12 of these in the GPT-2. The block has, as you can see, the positional embedding, the input embedding, and then they go through this multi-headed attention and feed forward. The add and norm are sort of reversed in this GPT-2, and let's see what's going on here. So there is the self.att is this multi-headed attention layer where the D in and the D out are the same, and they are 768, which is the embedding dimension here. And then there is a feed forward layer and some of the normalization layers and dropout. So what happens here is that we need to do the add and norm, which means that we get these embeddings, we calculate the attention embeddings, and then we add back the excess here. So basically what this means is that we have these X values, we get the Z embeddings from the self-attention, and we add back the X embeddings to the Z after the attention is calculated. That is what this figure is referring to. And I don't know if the illustrated transformer covers this. Maybe it does. We can take a look. Yeah, so this is exactly what is happening here. They add and normalize. So basically, we have the self-attention, and then these sort of embeddings are added back to the self-attention. And then there is a layer norm here. Set. Right. Okay. So we name X as a shortcut, and then we first apply a normalization layer, then the attention layer, and then the dropout layer. And then we named the original X as shortcut. We add back the original X to the input block. Just make sure that that is exactly what is happening here. Slightly different. The normalization happens first in our GPT-2 model. The normalization happens first, and then we do all of this. And instead of normalizing here, we just add here. So that's maybe a little bit of difference. But essentially, we're doing the same thing here. And then the next thing that we need to implement is this feed forward add and norm. So with this X, we now again do this shortcut. We normalize, make it go through a feed forward layer, and then drop out, and then finally add it back. So essentially exactly that, only the add and norm is slightly different. So we add, but we don't norm. So that is one single sort of transformer block, and that is exactly what is implemented here, which makes total sense. And now we can come to the GPT model, which implements this architecture which we went through here. Let's see what it does. GPT-2 model, token embedding and positional embedding, which we went through, and then dropout. And then we add like number of transformer blocks. We have 12 layers in this GPT-2, so we add 12 of these transformer blocks. And transformer block is the class that we looked at just before this. And then we have a final layer norm. And then we have a outhead. This is the linear function which goes from embedding dimension 768 to vocab size, which is 50,000 something. So 50,257. So it basically produces a 50,257 sized vector, and giving a probability between 0 and 1 to each of these words to each of these words, and then we sort of make a choice of which one to predict based on these probabilities. And so let's see, so the token embedding, positional embedding, and then these 12 transformer blocks, and then we have the final layer norm and the outhead. So we take the IDX, let's forget the batch size for now. It's 1 here, and then the sequence length. So essentially what happens here is that we pass this word, we have this text, and we convert this into a series of tokens. So I actually run this once. So you have this function called text to token IDs, which takes this series of words, converts that into tokens, and each token has a number in the vocabulary. So of the 50,000 tokens, like this is token number 46506 is the word select, and so on and so forth. And we take this vector of tokens, and then let's see what happens here. GPT2 model, yeah. So we take this vector of tokens, which is the length of the sequence, the length of these tokens, and then we find the token embeddings from these indexes. So there is a 768 sized vector corresponding to 46506 token. There is one corresponding to the 312 token, and so on. And then GPT model, yeah. So this one here, this line here basically converts these token IDs to, or token indexes to, these embeddings. And then there is the positional embeddings, which are, from 1, 2, 3, 4 to like the sequence length. It converts each of them into like each of these indexes into an embedding, and then we add these two embeddings, and probably there is a picture here which will help you understand that. But essentially this x1, that is what we're taking these number, like actual tokens, and then we are converting that to these x1s, and then we sort of drop out, and then we pass it through 12 transformer blocks. This is sort of these 12 transformer blocks layers. So in here it means input embedding plus positional embedding, which is basically what happened in this line here, and then the next line sort of passes it to these 12 blocks, which is what happens in this line here. And then there is this final norm, and this is just a layered norm, which is, we defined a layer norm somewhere. The layer norm is just, minus mean divided by variance. And so we do that. And then finally the logits is this outhead, which is this linear layer that produces sort of vocabulary sized output. And so that is basically what is happening in the GPT model. And yeah, that completes this video, and thanks for sort of listening to this long video. I hope I was able to help you understand how to code up a GPT model from scratch and help you get a deeper understanding of the GPT-2 model. And I will upload this notebook as well to sort of help you follow through. Thanks a lot, and in the next video I will probably cover the last sort of bit where we produce the next word and how we actually produce the next word given the GPT-2 model. Thank you.